Morning, everyone. Am I audible? Hello. Please let me know, okay, like I'm audible or not, and let others join. We'll uh, wait for another 2 3 minutes. Other students, did they get the link which I sent just now, or maybe they are joining in their old link? Mm, Good morning, Pramila. Um, mm, no. Others where they are. Uh, Please make sure your friends also they know the link that I am using this link today. I'm not using the old one, the old link today. Last class, we were doing plate girders, right? We were, let me see, plate girders. I think till a moment we had calculated the loads, concentrated loads with the, you know, this shear force bending moment. Okay, I shall start. I think I shall start. Nothing. Meeting is open. This is not locked. Okay. Good morning, Rajan Maling. I can see. Okay. Okay, meeting link, switch audio. Okay, no problem. Okay, last class, I think we have in the plate girders, this was the question of the on plate girder. This one. Okay, this was the. Wait, let me close this. This too. So this was the question which we were, I think, which I gave you in your this last class, the welded plate girders for a simply supported beam. We had started, I think, I guess we have started with this total factored load. Okay, let's see, yes, ma'am. Okay. So we had till where I think till the moment we had done this. This means asked you to maybe I asked you to calculate this shear force and the bending moment, because after we have calculated the loads, all this UDLs, how much UDL is there, life load, dead load, self weight, etc. We had calculated our shear force and the bending moment, maximum bending moment we have got to be 5976. Okay. Wait, one more thing. Hmm. 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 So the maximum bending moment which we had got was how much? Was this one? 5976. Okay. And the maximum shear force was 96. Then we have got this shear. We have calculated this bending moment and shear force. Now the next step which we will move forward with is the selection of the section, like what kind of, because since it is a plate girder we will have a eye section, right? So we will have flanges, we will have webs though. So we are going to design like what size of web and what size of flange, what size of this. Waiting in the lobby, Barney de Burma, unlock meeting. Okay, so this was the I section. So we have to design this plate girder, right? We have to design this. So we need to know the size of this flange, this flange and the web, such that all the shear force and the bending moment which we have calculated, that can be resisted by this particular plate girder system. Okay, plate girder. So for that we have to select the sections, what type of section. I section we know, but what sizes of section we are using. Okay, such that the bending moments, the shear force which we have got, the maximum values that can be resisted by the this one plate girder. Now for that we we will proceed in this way. We will find out the optimum depth of the girder by d is equal to mk. This is your m, which is your moment, maximum moment which you have calculated, and small k by fy to the power 0.33. The overall depth of the girder will be this much, mk by fy to the power 0.33. M we know just now we have got the maximum bending moment to be 5976. K, okay, Fy we know 250. Fe for Fe410 we know it is 250. Right. Now for K, what is K here? K, for K you have to do one thing, that is K is d by dw. Okay. Now what is, one minute. What is a K value? K value is d by t. Am I audible? Right. I'm audible. Lancy, Taraland. So this is K is equal to d by tw value. This K is your d by tw. Now, what is a d by tw? D by tw is your depth to the thickness of the web, which we must know that if this d by tw is greater than 200, then intermediate stiffeners are required in your head girder. Head girder was what I showed you in the first class. Head girder, like at the no, this is I section. If you see this on the side view, so stiffeners may be used here, right? But this stiffeners, whether you will provide, whether you need to provide or not, that is this one. If your d by dw is greater than 200, your intermediate stiffeners are required. And if your d by dw is less than 200, your intermediate stiffeners are not required. Now, for this question, since we are designing, we will assume that our in our display girder we are having no stiffeners. We are not going to use any stiffeners. Okay, so for that we know that d by tw should be less than 200, and if d by tw is less than 200, then only we do not need to provide any intermediate stiffeners. This intermediate stiffeners we don't have to provide that. Okay, for supporting this web portion. Yeah. So what happens? So in this question, we are assuming, let us assume that this d by tw is less than 200, and therefore let us assume it to be 150. Here it is assumed to be 150. You can assume it yourself. But if you want, it is intermediate. We are not providing any stiffener, so we are taking it to be less than 200, and we have assumed that our d by tw is 150. In page number 63, if you go, bias code 6.1. See here, this one. From here also you can see this value d by tw less than 200 when stiffeners, when transverse stiffeners are not provided. Then these values are, you if you forget, then you can see here d by tw is less than 200 where quantitative flanges along both longitudinal universes. From here also you can have an idea, but you should know generally that this is d by tw should be less than 200. Okay, so now we know we have assumed that our K value is 150, that means less than 200, so we are not providing any intermediate stiffeners. So now we can place this K value here after assuming. So we have got after assuming this much is our depth, overall depth of the girder. So what we can do is we can take it to be 1400 mm for our design purpose. We are taking the depth to be 1400 mm. That means this portion, this, this one is your 1400. Okay. Now we will assume the thickness of the web. This is your web portion now. This one. So this is your 1400. Now we will assume that this thickness. We will assume a thickness for this web. We are finding out the size of the web, right? So first of all, we'll find out the size of the web. So now we know the depth of the web. Now we will assume a thickness which is 12, which can be 12 mm if you want, 10 mm, 14 mm. So we are assuming here 12 mm. Therefore, size of the web plate becomes now what? 1400 into 12. This one 1400 into 12 of the web, the size of the web, this is 1400 into 12. Now the bending moment, which, okay, one thing, this is the web and this is the flange. Always your web, this is resisting the shear, and your flanges are resisting your moment. Okay, always your web resists the shears and the your flange resists the bending moment. Okay? So bending moment is resisted by the flange only. So what now? We got the size of the web, right? This is the size of the web. We have calculated this depth and the thickness we have assumed. So we have got the size. Now we will come to the flange part. And then we'll check whether our assumed section, which the size of particular size, that is okay or not for our calculated bending moment, which is required bending moment or the shear force. Okay, so here now for the flange portion, we have area of the flanges m gamma mw by fy into d. So in clause number 8.4.2.1, here you will see resistance to shear buckling. Resistance to shear buckling shall be verified as specified. D by Tw should be greater than 67%. So you see here what happened. D by Tw should be greater than 67 epsilon for a web stiffener here. So this should be when we are not providing a stiffener, then this D by Tw should also be greater than 67 epsilon. Here you see now we have got the area of flange. We'll find out. There's some issues. So you see here, area of the flange is how much? Area of the flange is m gamma mw, m gamma mw fy into d. Okay, so we know this is our moment, which we have already calculated, 5976. Gamma mw we know you will get from table number 5. Know this thing. Fy we know it is 250. D we have just now calculated the depth to be 1400. Okay. So now we have got it to be area of the flange is 18781.71. So this is the area of the flange. Now we will go to page number 18 in the IS code. Hello. This is the table here. We want our section to be plastic, so we will assume it to be class 1A, and it is we will this is a welded section. So B by TF ratio, this one you see here 8.4 epsilon, it should be less than 8.4 epsilon. So now if we check for the compression flange with welded section, we have B by TF is equal to 8.4 epsilon for plastic section. So B is equal to how much? 8.4 epsilon TF. Okay, we have calculated the we have assumed the sections of the web we know the size. Now we are going for the trying to find out the size of the flange. Okay, this one, the size of this flange is. So area of the flange we know it must be this much. The required area of the flange is 18781. Now, according to that again, now we'll find out the width and the thickness of the flange. So for that, we have found in the table 18, table 2, page number 18, that the compression flange with the welded section is how much? B by TF is equal to 8.4 epsilon for plastic section. Now B can be written as 8.4 epsilon TF, 8.4 TF. Epsilon becomes 1 we know because it is root over 250 by Fy, and our Fy is how much? Our Fy is already 250 we know. Here if you see epsilon value you will get here. Epsilon value is how much? This one 250 root over 250 by Fy, and we know our Fy is 250, so it becomes 1, right? So here it is 1, 8.4 TF remains. So now here 8.4 TF, area of the flange, we know how much it is. Area of the flange, if we see this flange, area of this flange is how much? This width of the flange, and this area will be this into this. So we have area of the flange is equal to width of the flange into the thickness of the flange. So area of the flange, required area, we know it is 18781. Width of the flange, we have got it to be this width of the flange is this entire portion, right? But in your this portion from the center of the web to this much is your how much? B value. Okay, this is known as B. Here you can see the figures here also. So this one I section when you're taking, this one is how much? Here B, all these are B. Okay, from the center to the this portion is your B. So width of the flange is how much? Twice B. This one twice B. Then we have thickness of the flange. Thickness of this flange will come out by this now. And to B, B we know how much it is, 8.4 TF. So we can place it here, and then thickness of the flange we will get to be this much, which we can assume it to be, we can consider it to be 40 our thickness. We will consider that means this value, our this is how much? This one is 40 mm. Okay, so now width of the flange will come out. Obviously, width of the flange we know how much it is. Area of the flange by TF. Since we know now the TF, we have assumed we can easily find out from this relation our width of the flange, right? So width of the flange will be area required by the thickness of the flange, and we got our area. Sorry, width of the flange to be 469, which we can therefore we can take it to be 500. Our area of the flange to be, sorry, width of the flange, this width of the flange to be 500. 500. Okay, now the size of the flange we know it is how much? 500 into 40. Therefore size we have got now to be this. Earlier we have previously we have calculated the size of the web, and now we have calculated the size of the flange, which is this much. Now what we'll do, we have, now we know the sizes. We know the size of this web, 1400 into this one. How much was the thickness? 12 mm. 14 into 12. This is 500 into 40. So this sizes we know now. Now, since we have assumed the sizes, what we are going to do, we are going to check the serviceability of this I section, which is the plate girder, whether it can resist the shear forces and the bending moments which are required load, according to the loads. This one, whether this can be resisted or not. It's not shear force they can give or not, and bending moments they can resist or not. We're going to check that. So now, serviceability, if we check serviceability from clause number 8.6, go again to clause number 8.6. We will see here. Clause number 8.6, serviceability. This one, you see here, serviceability when stiffeners are not provided, G by TW is less than equal to 200 epsilon. Web connected to flanges along. Okay. So we have not provided the stiffeners, so we have to be, it should be less than d by tw should be less than equal to 200 epsilon, and we have got that already. We have also assumed before, we had assumed before, okay, that without stiffeners we are designing the plate girder. Now also we have got here also that this without stiffener, this size of the web or the flanges which we have taken, these can, this is okay, and this does not need any stiffeners also. Okay, web stiffener. So therefore, and our thickness is also which we have provided the thickness. This assumed thickness here, this one, this assumed thickness is also correct. Okay, when this is b by tw, we have calculated our d by tw is less than 200 epsilon. Therefore, this a our thickness assumption is okay of the web. Now next check again we have to do about the compression flange buckling requirement 8.6.1.2. 8.6.1.2. This one. See here compression flange buckling requirement. In order to avoid buckling of the compression flange into the web thickness shall satisfy the following. That is when stiffeners are not provided, and we know our stiffeners are not provided, so our d by tw should also be less than or equal to 345 epsilon f square. Epsilon f, here you can see what is epsilon f, yield stress ratio of the web, which is root over 250 by fy, and fy we know it is already 250, so this will obviously become 1 now. So when this has become 1, what we got here, d by tw is equal to 116.66, which is also less than 345 epsilon f square. Okay, so therefore minimum thickness of the web provided is sufficient. These two checks you have to do for the web which you have selected is correct or not, right? 8.6 and 8.6.1.2. Whether your d by tw is less than 200 epsilon and 345 epsilon f square. Okay. Now, the next check which we are going to do is the check for the moment capacity for flanges. In table 2, page number 18, which we went at 10, we know d by tf is how much? D by tf is equal to, this is the width of the flange was how much? This one was 500, this one was 500. So B is how much? Half of the 500. This is B suffix F, B suffix F, okay, equal to 500. And so therefore this will be B 250 and this is 250. So B by TF will be how much? 250. EF is thickness of the flange. This thickness was how much? We got 40. So B by TF is 6.25. Therefore, section is plastic. You can see here if you want in the table 2, page number 18, this one, table 2, B by TF, B by B by TF equal to 6.25 we have got for plastic section. Therefore, it is less than 8.4 epsilon. So, it is plastic. This plastic. So, therefore, the section is plastic. Now, again, for the moment, again, for if you see the moment check here in page number 53, 8.4.1.2. Page number 53, you will go. Page number 53, this one. Now, in page number 53, you see here this one, 8.2.1.1 to 8.2.1.2, this one here. Your moment is what? BD, ZP, FY by gamma MO. So we have to calculate this now, the design bending strength MD. Okay, we will check that the moment which we have calculated for the due to the loadings, whether that is coming to be less or more than this design moment now after your knowing the sections. Okay, so here beta b is how much? Beta b is 1 for the plastic and compact section, and beta b is this much for the semi compact, but we have our section to be plastic, so beta b is equal to 1, this one here. Okay, so then comes your fy, we know 250 because of the Fe415 lower stress. Then gamma MO, from table 5. Here, partial safety factor, and now ZP. What is ZP? ZP is the plastic section modulus of the cross section. Okay, rest. So here, if you see, person, my voice is not clear. Hello. Now is it okay, Jocelyn? Hello. Am I audible to all? Am I audible? Audio is cracking. It's not clear. Hmm. Should not crack. Hello. Now. Now is it okay? Hello. Yes, ma'am. I'm unable to hear you. Any others? Do you have maybe? Yeah. Is it for all? My voice is cracking. Audio is cracking. Is the network over? Who are able to hear clearly? Anyone who is hearing the audio is clear to them? Hmm. A little bit is there. Try to what I'll say. I'll share the PDF also. Okay. For now, manage. Okay. Let us see. Maybe others. Maybe your network problem is there. Okay. Now, if you see here, this moment check we are doing now, where it was this one, beta B, ZP, Fi. We got these values. Only the ZP, that is the plastic section modulus of the cross section, is remaining. Now, how to find out your section modulus ZP? ZP is your, this is your Z axis, this one is your Z axis. Now, what is yours? Moment, you can say, of that is section modulus of this portion. Now it's good. Okay, okay, fine. So, this is your section modulus Z. Sorry, this is the axis, Z axis. Now, what is it? This we know this is uniform on the up top and at the bottom. This size is same of the section. Uh, it is uniform top and bottom. So we can find out. We can multiply it by 2, and then you see here this is 500. The flange area is how much? 500 into this 40, and the moment of this flange is how much from here from the center? This will be 20. 20 plus this one 700, right? Because this entire one was how much? This portion was 1400 from here to till here. It was 1400. So half of the 1400 is 700, this portion, that means. So from here, this area of this flange is 500 into 40. Now the distance from the center is how much? This is your 700 plus 20, 720. That's why it is multiplied by 720. Moment of the flange about z-axis. This moment of this flange about z-axis. So we have got it to be this much. Okay, that is a ZP we have calculated. Now we can find out the design moment here because we know all the values. Beta B, this is your beta B. Beta B is 1, ZP is our this much. This one we have calculated ZP, Fy we know 250, gamma MO we know from table 5. Now we have seen our moment is how much? 654 0.45 into 10 to the power 6 Newton mm. So this is the design moment, and our maximum bending moment was how much? This much. So obviously when our design moment is greater, it can take this much of moments, which is this, and this one was the maximum moment, okay, due to the loading. So obviously this is design, our design and the sizes of the web flange whichever we have considered, it is okay, it can resist this much of moment, it can carry this much of moment easily because the moment, design moment, is very much high. Now next for the, we will check for the shear capacity, okay, of the web. Now we, for this we have to go again to page number 59. Now if you see here in page number, this one, 59, okay, we know what for our nominal shear resistance is how much? Vn. This one, V should be less than Vd. Vd is Vn by gamma mo. Vn is how much? Vn is your Vp. This one, Vn is equal to Vp. But what is your Vp? Vp is Av Fy by root 3. This one. So, Av Fy by root 3 gamma mo. Sorry. This one. This one, gamma mo. Okay. So, when we place these values, what we get? When we place these values, Fy we know, root 3 we know, gamma mo we know 1.10. So AB is how much? Area of the shear. I told you that the shear is carried by what? The shear is carried by the web. So the area of the web should be required, and this is the area of the web. We know 1400 into the thickness of the web, 12. So this much, and also the factored shear is how much? 0.6 VD. So which is again greater than 996, which is the maximum shear force. So obviously it is our, again, the thickness of the web assumed is also okay for our design. Why? Because our factored shear force is greater, very much greater than our maximum shear due to the loading. Right. Our next is what? Our next check is the check for shear buckling of web using the simple point critical method. Okay. So here it is in page number 59. If we go, okay, again here. Yeah. You see here, shear buckling design method. So we have the nominal shear strength of the webs with or without intermediate stiffeners as governed by buckling may be evaluated using one of the following methods, which is simple post critical method, or you can see here another method is the tension field method. So we are going to use, okay. So since we are not using transverse stiffeners, so we will go with the simple post-critical method. So here you see Vn is equal to Cr. Now what is, to find out the nominal shear strength, we have to calculate nominal shear strength, which is given by Vn. But what is Vn? Vn is equal to Vcr. And what is a VCR? VCR is your shear force corresponding to the web buckling, and that is area of the shear area, which is your area of the web, into gamma tau b. And what is your tau b? Tau b is the shear stress corresponding to web buckling, which will be determined as, which you can determine by either this from this three of the following. Okay. For to find out tau b, you have to know lambda w, which is the non-dimensional web slenderness ratio for shear buckling. Okay, so now to know this, once you know the lambda w value, then with the help of this lambda w value, you can know what is the formula you're going to use for your tau b, the shear stress corresponding to the web buckling. Okay, so therefore you have to find out lambda w. And now what is lambda mw? Lambda w is root over fy by root 3 tau CRE. Now, what is to find out lambda W? Again, you have to know tau CRE. Now, what is a tau CRE? The elastic critical shear stress of the web, which is given by kV pi square E by 12 1 minus mu square whole into d by tw whole square. Okay, so from here we know Poisson's ratio 0.3. We know kV. kV is how much? 5.35 when transverse stiffeners are provided only at supports, and we know we have only at supports, we don't have intermediate stiffeners. So kV value we have got from here 5.35. This kV will be 5.35. E, you know, it is what? 2 into 10 to the power 5. Then we have mu, the Poisson's ratio 0.3. D we know, TW we know. So once we know tau CR, once we know this tau CR value, so you see here we are trying to find out the tau CR value, elastic critical shear stress first of all, and then you see here kV is how much? 5.35 from the IS code. Then we have E is 2, 2 into 10 to the power 5 elastic constant. Then we have mu 0.3. D we know of the web is 1400. Thickness of the web is 12 mm. So we got the tau CR value to be 71.04 Newton per mm square. Now with the help of this we can find out the lambda W. Putting the value of placing the value of tau CR, we can calculate the lambda W. Now you see lambda W is greater than 1.2. If you go to again IS code here, lambda W value. Now you see here once you calculate the lambda W value, you have to see which condition is satisfying to select one formula for tau B. So we see here how much we got. Our lambda w is 1.425, which is 1.425, right? 1.425, it will be this one, this condition, lambda w is greater than equal to 1.2. Therefore our tau b will be how much? This one, fy by root 3 lambda square. So we are going to use this formula here. You see here, that's why we have used this formula.